Right. So at the end, I'll give an example of a real world application with ballistic tracking. And you see that the particle filter part is actually the easier part. The harder part is actually to set up the problem, figure out all the equations, the dynamics, all of these aerodynamics terms that you need, and try to like force it into the standard framework for particle filters. So the particle filters in real life, even for common filters, the application of these filters is really the last part of your problem. Before that, you have this whole the big engineering issue of how do I take real world data, how do I take a real world problem and fit it into the assumptions that will work for these frameworks. Okay, so homework 4, I will give you guys a problem where you have to implement the particle filters or sequential importance sampling. So here on the screen, this is like basically the algorithm that you need for it. So again, in order to do this, this is a Monte Carlo method. So you have to generate some number of particles. It doesn't have to be, it could be 100, 1,000. It does, you don't need to like generate 10,000 in the beginning. And then what we have to do is we have to have some initial assumption of how to start the initial state, right? So either we just start, say the initial state is 0, or we assume we can draw it from some probability distribution. And then we also have to initialize the weight of every trajectory to some number, right? So this is all the initialization. And when we implement the algorithm, we have to decide what is the importance distribution we're going to use. So the one I covered last time, the simplest one is, I call it the SIR, sequential importance resampling, but it's also known as the bootstrap algorithm. So in that case, the importance sampling I want to use is the probability of xn given xn minus 1. So the state transition probability, which you should know. And I'll show you examples where the way you would know this is because you actually know something about the dynamics model. So it's like the state space, the xn equals some function of xn minus 1 plus noise. So from that you can derive what this probability of xn given xn minus 1 is. If you don't have that, it's kind of like take your best guess, right? But if you're working on a problem where it's very difficult to come up with this, then you may have to learn this probability distribution from data, and that is very difficult to do. But so in standard scenarios, like with tracking or any sort of problem involving physics, like you're actually following the dynamic of an object through the air, because of physics, we actually have actual dynamic equation to use. But if you're trying to do something where it's like the probability, the conditional probability of stock price, well, there's no underlying physics to tell you how that thing will change. So then your problem, a lot of the time, that's going to be difficult, is to know what this probability is, what this conditional probability is. And then today we'll talk about, in addition to the simplest type of importance distribution, there's also one which is called the optimal importance distribution. So that's a slightly different conditional probability. That's the conditional probability of the state at time n, given the state, the previous state at time n minus 1, and also the current measurement at time n. So the simplest one doesn't include any information from the current measurement. The optimal importance function does include this current measurement. So, but that said, then this is a more complicated probability distribution, and so therefore you might not know this in your actual problem. But the idea is, once you have decided, depending on what you know in your problem, on what is your importance distribution, then hopefully these are Gaussian, right, or some standard simple probability distribution. Then you can just go to MATLAB and then tell MATLAB, here, just keep generating R samples from this probability distribution. and then you can compute the normalized weight of this distribution, right? So bear in mind that this term with all the probabilities in there, that's the incremental weight, what is it called? The incremental weight update or something. So it's the term that updates your weight from time n minus 1. Oops, that should be n. From time n minus 1 to n. So because we assumed very specific forms for what the importance distribution is, which is this denominator here in this term, we can start canceling things, right? So if the denominator, if the importance distribution we choose to use is the state transition distribution in the bootstrap, you see that term cancels with one of the numerator terms. So the only thing you're left with is the likelihood, right? So depending on what you choose as the importance distribution, this incremental term for the weights will be easy or hard depending on that. But basically then you have the weights and you assume that you have the normalized weights, and then after that the idea is to resample the particles according to the normalized weights, right? So the particles with the higher normalized weights presumably gets resampled more than the particles with the lower normalized weights. And then the next thing is, since after resampling, you just update the weights again, so it's 1 divided by m, right? So then the idea is you repeat this all over again for the next time step, and so forth, right? So every time step you get, so I say time 5, you get, say, 100 particles. So once you do the resampling, you can take the average of those 100 particles, and that is your estimate of what the state is at time 5, right? So you can either keep doing this time by time, or what you can do is you can wait until you have the particles from time 1 up to, say, time 20, and then you take the average of those sequences, and then you will have the particles from time 1 to time 20, right? So you can either do it time by time or the entire sequence for some finite period. Okay, so now I'll give you an example with an actual model. Okay, so can you see my tablet now if I write instead of the code?
Yep, we can see it.
Okay.
Yes.
So here, this is a toy example, right? So I don't know what physical system this corresponds to. So our state space model is my dynamic at time, my unknown state at time n is half times the state at time n minus 1 plus 25 x at time n minus 1 divided by 1 plus x minus 1 squared plus 8 cosine 1.2 n minus 1. I think I made a mistake there. I think this is what I meant to say. There's a typo. Okay, plus Wn. So that the Wn is noise, right? So this is clearly a nonlinear function of x of n minus 1, right? If I had only this term, then this would be a linear function of x n minus 1. But I have this entire mess here, so it's clearly a nonlinear function. Okay, and then the measurement, also going to assume is 1 divided by 20 x of n squared plus Vn, right? So this is also a nonlinear measurement function. And of course, we have the dynamics noise and we have the measurement noise. So I'm going to assume that the dynamics noise is Gaussian with mean 0 and variance 1. So here we're going to assume the simplest case that these are scalar values. This is a number and this is a number, right? So that's why instead of the the covariance matrix, we just have a variance. And then the measurement noise is also Gaussian with mean 0 and variance 10, right? So this is the model that I know, or I managed to simplify my problem to such a model. I just know these things are nonlinear. So therefore, either I use extended Kalman filter to linearize this, and then use extended linearize this, and then basically use the standard Kalman filter, and that procedure is called the extended Kalman filter, or I use particle filters, right? Okay. So the particle filters, again, I have to start, it's like the initialization process. I have to have some idea of where the initial state is. So this is either known, assumed, guessed, whatever. However you get an initial state, you have an initial state. And then, so then what I do is I use the implement the particle filter algorithm, so sequential importance sampling or particle filter. So the algorithm I showed you before. So I have to decide how many particles I need, right? So this I have to decide. So the decision of how many particles you need, this is actually not trivial in the sense that it's not easy to know the optimum number. So you could guess, of course, you could say, well, I don't want 2 because that's too small. I don't want 10,000 because that's too big. So I might as well do like 500 or something. But for sure, there is actually, if you were actually able to know the true solution, there is an optimal number that you can pick. And there's actually research, a lot of research in finding the optimal number of particles that you can pick. But that's very difficult. It's a very difficult problem. So it doesn't work in general solutions. So here you could say, well, I'll just pick, some number, say 100 or 1,000. Right. So some number which is to your limit of your computation power. And then also, so we're going to use the simplest particle filter, right? The simplest particle filter, which means that the importance distribution I'm going to use, right, it's going to be just a state transition distribution. So this importance distribution, which can be as fancy as this thing, but this thing is really hard to know what it is, I'll just use the state transition distribution. Right. And then I implement this algorithm. So at each time step, I draw particles from this distribution, I find the weights, then I do resampling, and then I go on to the next time step and so forth, right? So, but that said, what this means is, in order for me to generate samples from this, I need to know what is this distribution. Right. So if this is my model, right, this is my state space model, then what is the probability of xn given xn minus 1? So how would I begin to find this probability distribution? If this is the state space model, and I didn't make any assumption about what this is, how do I look at this and come up with this?
It's a Gaussian distribution.
Why?
Gaussian distribution.
I know, but why?
Because we have no xn minus 1 now, so xn just associated with wn.
Okay. So right. So you notice. So that's true, right? So here in this term, this is a known number, right? As soon as I know what xn is, I know exactly what this value is. So that means the only thing is that's added to the unknownness of xn is this noise term, right? And this noise term I know is Gaussian. So whatever this number ends up being is some number, some fixed number plus a Gaussian noise, right? So therefore, the probability of xn given n minus 1 has to be Gaussian, right? So then in order, if it's Gaussian, then I know that for me to specify it, I need to know the mean and I need to know the variance or the covariance. So in this case, what is the mean of this Gaussian?
Is it going to be whatever the value of xn is, essentially without the noise? Everything to the left,
Yes.
WN?
Everything to the left. So you mean this term?
Yeah.
Okay. So, okay, so let's make this concrete. If I know, so this is really a given, right? So even though I don't write it this way, this is really like, say, a number given 10, right? So if this thing is 10, then how do I compute the mean? So using your idea, you said everything left to WN, okay? But if I now, just to make it more specific, so we, instead of just using variables, we actually tell you the conditioning value is the number 10. What is the mean of this probability distribution? We know it's a Gaussian, so what's the mean of that?
Would it just be 10 times whatever Christian said on the left side?
So you mean 10 times 0.5 xn minus 1 plus 25 xn minus 1, like this whole mess?
Yes.
Okay, but this whole mess here, I don't actually know what this number is, right? Because what's xn minus 1? You tell me it's 10 times 0.5 times xn minus 1, but I don't know what, like, what's this value, because I still don't know this number.
Don't you just plug in 10 for x of n minus 1?
Okay, so then in that case, what's my mean?
It's that whole thing with x of n minus 1 equals 10. So
Right.
Some number.
Exactly, right. So you're right in that the mean is this, but just to make it concrete, this depends on the value of xn minus 1. But when I look at this conditional, I actually do know the value of xn minus 1. So it's 0.5 times the value of xn minus 1, which in this simple example is 10, plus 25 times xn minus 1, which is also 10, divided by 1 plus xn 10 squared, right, and so forth, right? So I actually do know this, except when I write the math, I don't normally write it as given an actual number, I write it as given a variable. So, but that's the mean, right? So that's why when you see I write, sometime I will write xn given xn minus 1 superscript I, right? So what that means is, what does it mean if I write conditioned on xn minus 1 with a superscript I?
You're choosing a particular value of x of n minus 1, and it's not the entire random variable.
So yes, except the superscript I is not, it's not just a particular value. When I talk about particle filters, what do I mean? Right, it's not just, I just pick a, it's not that I know it's conditional on a variable, so I just pick a random number, say 5, and I'm done. Or I pick a random number, or I pick a number, say 7, and I'm done. So this notation actually means something very specific.
Is it sequential?
Is it like the ith sample?
Right.
Okay.
So the ith trajectory, right? Or the ith sample, the ith trajectory, or the ith particle. Right. So the thing about notation is it usually I know it might seem inconsistent that sometimes I write this and then sometime I write this. Right. But this again, it's any general variable xn. So it might be that this is 10. But when I write this, then what this tells you is that it's conditioned on exactly the value of xn minus 1 you get for the ith trajectory. So it could be that the value of xn minus 1 for the second trajectory is 10, but xn minus 1 for the third trajectory is 8, right? So this value will change depending on what the trajectory is. So when you see this with the superscript I, it's saying makes it explicitly dependent on the value of xn minus 1, but for that particular trajectory, right? Okay, so but you see that when I look, I know that this thing is Gaussian, and I know the mean is nothing but plugging in what the actual value is of the conditional for the mean. And the reason that's the mean, so why is the mean only dependent on this term and not Wn? Right, because technically Xn is both this mess plus Wn, right? And Wn we say is the Gaussian noise. So why does the mean only depend on this term?
Because our noise is zero mean.
Right. So we make this very specific assumption that the noise has zero mean. So that's why the mean here only really doesn't reflect anything about W. That's because we're adding this whole mess plus 0, which comes from the mean of your noise. So if you're working on a problem and the mean of the noise is not 0, you have to account for that in the mean of this Gaussian, right? Okay, so we have the mean, and then so what's the variance or the covariance of this probability distribution?
It's just the identity matrix.
Or I guess like where do I find that, or how do I find that answer?
From your noise again.
Right. So in the noise, so this is a fixed number, so it has 0 variance. But the noise, and because this is this thing plus this thing, the noise, the variance of this distribution is going to be the variance of my measurement noise. And in this case, again, it's a scalar, so it's a 1. But if it was, a non-scalar value, it would have been an identity matrix. Okay, right. So you see that in this simple example, right, from the state space model, I can actually derive what the importance distribution is, right? So I know that now when I generate my sample, I'm going to be able to generate my sample from a Gaussian distribution with this mean 0.5 times xn minus 1 to the ith part of the ith particle. Right, it's that long complicated expression. But because this is Gaussian, you go into your MATLAB, you tell MATLAB what the mean and what the variance is, and MATLAB is happy to generate any number of samples from this distribution, right? So now in the first part of the algorithm, you know how to generate the samples. So the next thing is to find the normalized, the weights, right? So again, in the initial case, every particle has a particular weight. So initially, all the particle has the same weight, which is 1 over r, or you can set it to 1. It doesn't matter. The initial weight you can pick to be some constant number. So you can just choose to be 1 divided by r. But we know that the weight updates. Right, the weight is, so the only issue is because you're talking about normalized weights, this term normalizes the weight. But otherwise, it doesn't really matter. It's the previous weight term, right? So in the beginning, this term is just some fixed number you choose. So in the second step, you'll see it will be updated. So this thing is going to be updated according to my incremental factor, right? So again, this is the most general form. For the simple example, we said that we're going to pick the bootstrapped importance distribution. So instead of the general importance distribution, we say that that's going to be this Gaussian, right? This state transition, which we know is a Gaussian. So in that case, then this thing changes to the probability of xn given xn minus 1i, right? And we can see that when we do that, we have cancellation between this term and one of the terms in the numerator, right? So that means that in order for me to update my weight, aside from having to normalize, what I really need is the likelihood distribution, right? So the probability of observing the measurement at time n given the state at time n, So now I still go back. Oh, that's not the eraser. So now I go back and I look at my measurement model. Right, and I know that what I want now is the probability of yn given xn, right? So again, suppose that the probability of yn given xn equals to 10. So how do I look at this and determine what is this probability distribution?
Just the same as before, you put in xn equals 10 to find the mean, and then the variance from the given noise.
Okay, so this is, so are you saying, is this Gaussian? Is this Poisson? So first, is this?
Gaussian.
Okay, so it's
Yeah.
Gaussian, right? So it's Gaussian, so it's because it's Gaussian, that's why the only thing we need to know is the mean and the variance, right? If it's some other probability distribution, there's some other parameterization for this distribution, right? So while it's true that the mean and the variance are the thing we usually find the most, just know that it's not the only information. It's only true, these are the only information we need because we're playing around with Gaussians. Okay, so you're saying the mean is now, again, the same thing where I plug in x of n equals to 10. But to, so which one of the, I have two equations, right?
Oh, the bottom one.
Okay, right, exactly, right. So the mean is going to be exactly the same thing. We know it's Gaussian because when we look at the measurement equation, we have some number plus the measurement noise. So that's why the probability of y given xn is a Gaussian, because the measurement noise is Gaussian, right? So again, the mean of the measurement noise is 0 plus this term, which is dependent on what xn is. And what in this case, we say xn equals to 10. So this is 1 divided by 20 times 10 squared, right? And that's the mean in this case. In general, it will be 1 divided by 20 times xn squared, right? And also, what's the variance?
Variance is 10 this time.
Right, right, because we're working now with the measurement noise. So in this case, the variance attributed to the measurement is from the measurement noise, which in this case is 10, right? So I also know from this that this probability is going to be right. This is a Gaussian, which mean 1 divided by 20 times the state of the ith particle at time n with variance 10. Okay, so so this is a probability, right? So I'm now drawing samples from this, right? Unlike the the previous distribution, I told you this is the Gaussian. The point of the sequential Monte Carlo is you're actually going to ask MATLAB or Python, whatever, to generate samples from this. So now that I'm working with this, I know that it's a Gaussian with this mean and this variance, but what am I getting out of this? Like, what is the part of, why is it that I need to know this probability distribution? Is it because I want to generate samples from this?
For every sample that is generated, you need to figure out what weight to assign to it.
Okay, so that's W, right? So if for every sample I generate, I have to figure out the corresponding weight, which is W. So this likelihood distribution is part of this computation for W. So my question is, what am I getting out of this? Like, how does this help me with the W? Because this is the problem. I just figured out that this thing, this likelihood function, is a Gaussian distribution. But how am I supposed to use this?
Well, as you're generating the samples in the step prior, that generates an X and an N.
Okay, yes.
And so, and then you take that and you're essentially saying, for this sample that I generated, what is its actual probability value for Y?
Okay, right, which is what this thing is, right? So I guess what I'm saying is, when I see this term, am I expecting a probability distribution here, or am I expecting a vector? Am I expecting a number? Am I expecting a matrix?
You'll want a discrete probability that's the same shape as whatever your actual samples are. So whether it's a scalar input, scalar output, or vector input, vector output.
You're telling me that this thing can be a vector, or this thing is the same dimension as yn. So suppose yn, like, you know, like, we'll make it easy. So suppose yn is like 2, 3. So you're saying probability of yn x and I is some number and some number.
Yes. Or no.
It's
Does somebody
dependent on
wanna-
epsilon.
So you're telling me the probability, I mean, I'm just putting numbers, right? So probability of 2, 3, given, say, make it simple, we'll make x in like a scalar. So given 5, this can be, say, 0.1, 0.3.
No, it's a scalar.
It'd be a single probability.
Right. So one thing about probability is, regardless of what is this guy, it always has to be a number, right? It's the probability of this thing, right? So probability of 2, 3 has to be a single scalar, right? So that's the thing. Here, you should expect a number, right? And it makes sense to get a number because the weight is a number, right? So associated with every xn, every sample. So the confusion part might be, you can see that the sample I generate could be a vector, right? It could be, it doesn't have to be a number, it could be a vector. But associated with every sample is this numerical weight. So that has to be a number. So that means that every single term in here has to be a number. So this is the probability of seeing this particular measurement, which I know because I'm seeing it, given the sampled state, right? So regardless of what the dimensionality of the measurement or the dimensionality of the state, this thing has to be a number, right? And the number comes from a Gaussian distribution. So the probability of this at time yn is my new measurement given what I just generated from the previous step. This gives me the likelihood, which is a number, right? Okay, so then, you know, once you have the normalized weights, you do the resampling, blah, 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 and then you keep going forward, right, in time. So you see that, at least with this simple example, it's not so difficult to find the necessary components you need, right? Everything turns out to be Gaussian, which we know a lot of, and it all comes from this state space model, right? So coming up with this state space model is actually, in most cases, your most challenging task. Not in the, if you are able to come up with a problem that fits this scenario, it's really easy, is what I'm saying. As long as you can figure out what these probability distribution is, right? So you see that there is a reason why everyone likes to use this bootstrapped this bootstrapped importance sampling because of this nice cancellation, right? So instead of having to work with a probability times another probability divided by another probability, all three of which, well, at least in the bottom one, which I might not know, is much easier just to work with one probability and get a single number, right? I don't even have to do any multiplication or division or division here. So that's why the bootstrap algorithm is the easiest to implement and also the most popular. So what you can see is, so again, because this is a toy problem, we actually know the ground truth, right? Like we can generate the ground truth, have a bunch of measurements and so forth. So here, the black line connected over time, right? This is really discrete, is the true time, the true sequence over time. So obviously this is a nonlinear sequence, so you see things are weird. And then the asterisk, the right asterisks, these are the states that we get by estimating, this is with 100 particles, the state we get by taking the average of all 100 particles at a particular time, right? So you see it does pretty well. Sometimes it's a little bit off, but in general, it tracks pretty well. So if you try to do this with common filters, it's going to be going all over the place. So the dashed line is the maximum and the minimum of the generated particles. So you can see that the particles it generates out of 100 different samples, it may not exactly be closely on the dot of the true value, but the average of them should be within, should be close to the true value. Right? So, and just to show that, so the number of particles, it's actually, there's a lot of work on analyzing that. So, sorry for this terrible photo. So here, because we know the true, this true sequence, we can find the mean square error between the true sequence and then our predicted average, our predicted value, right? Our estimated value, the asterisk. So what we can do is we can do that and plot against the number of particles. So obviously, if we don't have that many particles, we're going to be way off, right? We only have one trajectory. It's very unlikely to be exactly the same as the true trajectory. So we do know that as the number of particles increase, our estimate and the true value should be similar. So the error should decrease. But what you can see here, since they did it for many cases, is that sometimes it will start leveling off. So that's why in the book example, they picked 100 to be the number of particles, because really you can pick 500 and your error is not going to be any better than if you pick 100. And you're going to do way more computations when you pick 500, right? So there's no point. So you might as well pick 100. So this is for a toy problem. We know the true optimal number of samples to use. But in general, we don't. And there's a lot of open research as to what is the best way to find the optimum number of particles. Okay. So that should give you, some idea of how to implement the simplest type of particle filters when you have a very basic importance function. So that said, that is also one of the worst. So because it's so simple, of course, the trade-off is, the simplicity is you're also actually going to probably have the worst performance. So this is, sorry, yeah. So this is the true importance sampling. So we're going to assume that instead of this, we're going to use this transition probability, this, right? So this actually turns out to be, it's the simplest choice, but also the worst. Right. So we know that if we choose this as the importance sampler, then when we do the weights, right, when we update the weight, it's going to be the previous weight times the likelihood function, right? So if we choose this, then this is going to be our weight update equation in proportion to, because it's a normalization constant. But the whole term with the products and the division, things cancel out, and the only thing we need to find is the likelihood distribution. So, but this is the worst in terms of performance. And can you see why this might be a bad idea? So this is the distribution that we generate sample from. Right. And this is the distribution associated with the weight of the sample. Right. And you can see that these distributions, in general, have nothing to do. I mean, they do have. They are from the same state space model, but can you see a reason why it might not be a good choice to work with this bootstrap filter?
Is it because it doesn't take into account any of the previous observations? Or yeah, state.
That's overthinking it, in the sense that, I mean, I do, right? I definitely take into account of the previous states. But if you're thinking, okay, it doesn't take into account of xn minus 2, well, it doesn't. But in most cases, that assumption is pretty good in that the time decay is pretty fast. So if we do take it into account of xn minus 2, it may give us a little bit of a boost, but in general, you will see, for the price you're paying in terms of computation, you probably see very little gain. So it's not a subtle reason like that. It has to do with that if I choose this particular distribution as the distribution that I sample from, then I have to use this distribution as the distribution of the weight. And I wonder if you see that maybe there is a condition where, because if I pick this, I'm fixed to this. And if you see, there's a reason why it might be a bad choice.
Could it correspond to a different trajectory?
No, in the sense that if this is the Ives trajectory, I'm still working with the Ives trajectory. I can't suddenly switch to the I+1 trajectory.
So is the like Rth weight for the same trajectory?
Oh, sorry. Yeah, because sorry.
Okay, I see.
Yeah, sorry. I meant to. It's hard. Sorry, I'm using different books, so even in the notes is a little hard to stay consistent. Yeah. So in this case, the everything is the same trajectory, right? The sample I generate from is the same trajectory. The weight is associated with the same trajectory. But do you see a way, like I could be doing a lot of extra work when I do importance sampling, but it might be a lot of work that is useless? It's like that the particle degeneracy, right? Recall the reason we do this resampling is not because we enjoy doing resampling, because it takes time, but because we do resampling in order to get rid of particles which have very little weight, right? Because remember, when you take the particles, you're supposed to do if you don't do resampling, you're supposed to do a weighted average, and the weight is the normalized weight of the particle. But if a particle has like almost close to zero weight, then it doesn't really affect the weighted average very much. So here, do you see when that might occur? So look at this, right? So when I generate this distribution, right? So again, like the example, this is a Gaussian, right? So this is xn. So this thing is going to be more likely to generate, so suppose this is like 10, and then 9, right? So whenever I ask MATLAB to generate a xn value from this distribution, it's most likely going to generate a number around here, right? So the first time I generate xn, it might be 9.7. The second time I generate xn, it might be 10.2. Third time, it might be 11.5. Fourth time, it might be 10.3. Right. You see that if I generate from this, this is the type of, most likely the type of samples I will get, right? So but that's only the first part of the problem. The sampling, clearly the generating part is no problem. But now I have to associate it with the weights, right? And the weights is updated according to this distribution, the likelihood distribution. So do you see when the scenario when this thing could be bad, or it's a state I would like to avoid?
Like when xn gets too far away from the mean?
Well, but that will happen, right? I mean, because you're asking a random generator to generate from your known Gaussian distribution. It's very likely that this could be xn like 50. But there's nothing you can do about it, because that's the nature of random generation, right? Maybe once every 100 times you'll see like a 50, but that's not what could go wrong. At least it doesn't matter to the particle filter algorithm to get these values, right? These are still the right generation, assuming the MATLAB code for generating Gaussian samples is good. These are still the correct samples that is generated. No, the thing that can go wrong is here. So what do you think is the worst case scenario when I start thinking about the weights?
If we had a previous weight, like a weight for n-1 that was really low based off whatever the previous sample was, but then our current sample is something that's high probability, both for the x and for the y, we could throw out that current sample essentially because when we update our weight for it, it might still be relatively anyways very low, even though it's actually a good predictor.
So when you say when the probability of y and like when you mean this probability, because you said probability of y and the probability of x.
Like say we got 50 for n minus 1, so our weight for n minus 1 was pretty low,
Okay.
but now this time we get 10, and based off of whatever our y is, say 10 is ended up being a good predictor, so the probability on the right side, the yn of xn. But based off my previous weight, because the previous number was 50 and I was way off, that previous weight could be really low and cause me to throw out this trajectory, even though this time it was good, but previously it was bad due to the low weight.
Okay, you're getting there, but I think you're overcomplicating things. So for you, you're thinking, oh, there is something that I can mess up with the weights. So so make it simple. Why don't we just assume that the weights are what it is, right? You get somebody give you the previous weight and it was computed good. Like the previous weight is what the previous weight is. The only thing you get to change about the previous weight is you update with this term, right? This conditional likelihood, this likelihood function. So don't think about how this whole chain of effect of when things can go wrong from the previous way to, like this whole thing. But just think about if I take the weight computation as is, which is the previous weight times the likelihood, and discount the fact that the previous weight is good in that respect, what is it that I can do? So the previous weight could be high, right? And you say that the current weight could be low. So how would that work? Like, why would the previous weight be high, but the current weight be low?
If our current y is a bad predictor of our current x.
So you say this in English. So when you tell me the current y is a bad predictor of my current x, I feel like you're telling me this. The conditional probability of xn given yn, right?
Other way around.
Right. So how would you say it?
Conditional probability of y given xn.
The likelihood, right? So the likelihood of observing yn given xn, right? Or yeah, so this is the likelihood. So if this is high, if this number is small, then it will make the current weight small, right?
Yes.
Okay, good. So I'll take it. So the thing is, when you generate this, you generate according to this transition probability, this xn given xn minus 1. But it could be the case that this state actually gives you a very low likelihood, right? Because there's nothing here. This distribution is unrelated. This distribution does not take into account of the observation, right? When I generate my state, I don't take into account of the current observation. So it might be the scenario where I generate a bunch of particles which are extremely likely in this probability distribution, but for which has very, very low likelihood function, right? The probability of yn given xn1 equals to 10.2, this could be very low. This could be 0.02. This could be 0.001, right? The probability of yn given 11.5 could be 0.0005, right? So that's because when I generate this thing, it doesn't take into account of the measurement, but when I go compute the weight, I have to use the likelihood function of the measurement. So I could be undoing all my good work if I'm working in the problem with a sample generating distribution, which is, you know, in some sense wide, in that I have a lot of particles which are I generate a lot of samples which are highly likely, but for which it gives me a very small likelihood, right? In which case my weight is going to be very small, and I'm basically generating all these particles again for not very much gain, because the weight tells me these particles are highly unlikely, and I'm not going to end up using them, right? So it's again that effort of I'm wasting my effort doing all of this Monte Carlo stuff, but because the generating distribution doesn't take into account of the current observation, I could be undoing all my good work, right? So that's why the optimal importance distribution, or the optimal importance function, is one which does take into account of the current state, the current measurement, right? So this is the general form of the importance function. The optimal one is probability of xn given the past state, but also the current measurement. Right. In which case, then this will guarantee that I don't have this problem, right? Because a xn, which is highly likely given a particular measurement, is also going to give me a high probability of the measurement given the state at time n, right? So that's why this is the optimal. But the downside of this is this update term becomes a little bit more complicated. So the general update term, so let's see, so the weight, so if we ignore the normalization function, the weight update is the previous weight times this update function, right? So if in the bootstrap algorithm, this thing is very simply the likelihood function. Here we have to recompute it. So this thing in general is the likelihood. Sorry, it's the state transition times the likelihood divided by the importance function. Right. So this is the general form. So again, here we're going to replace the importance wrong one. The importance distribution with the optimal importance distribution. Right. And then the idea is we should be able, so you see there's no clear cancellation anymore, like with the simple bootstrap filter, right? Like these terms look similar, but they're not identical. I mean, they're not the same distribution, so you can't just go around canceling things. So then you're like, okay, I need to do some math. So this is where you need to know your Bayes rule really, really well. But the thing what you see is when you do, let's see, what you can do is you can use Bayes rule. Oops. You can use Bayes rule on the denominator. So you can actually you can break this denominator up. The hope is that you can break the denominator up in such a way that you can cancel with some of the terms in the numerator. So the denominator, right, I can write this using Bayes rule. And then I can start, this is just the general base rule of the joint divided by the conditional, the probability of what's given. But then I can further simplify this by using base rule, right? So what I can do is, what I want to do is I want to keep writing these into forms where I know things will try to cancel, right? And a lot of the times this actually, there is, you know, it's not always clear. There's so many ways you could break these terms up into conditionals. It's not always clear this is the way to do it, but that's why you have to spend some time at this. But ultimately what you can get is you can get this, right? So the denominator, my optimal importance distribution, I can get into this form. And you see the reason this is nice is because the likelihood function is here and the state transition distribution is here. And these two things are going to cancel with the numerator term in gamma, right? So now gamma right? And then I have this whole thing in the denominator, right? These things are going to cancel with each other. So now I know that my weight update, instead of being the likelihood, right? The likelihood is the probability of yn given xn, is going to be this, which is, it's a conditional distribution. It doesn't have a name. It's the probability of the measure of time yn given the measurement, the measurement of time n given the state at time n minus 1. Right? So this is what I need to update the weight when I use the optimal importance function. So because while it might look, the difficult part is sometimes we may not be able to sample from this. That's the only thing, right? Because if you look at the other problem, this is this might not be a simple Gaussian, is the thing. So that's the only reason that keeps us from being able to use the optimal importance function. Let's see. So there is a case, there is a special case when we do get a closed form optimal importance function, and also this weight update term, probability of yn given xn minus 1i. And that case is if we have a nonlinear state dynamic, but a linear measurement model. So for example, x at time n is some nonlinear function of x at time n minus 1 plus some noise, which again assumed to be Gaussian. So in general, we have some covariance matrix, zero mean Gaussian with some covariance matrix. But the measurement model is going to be a linear function of the state. Okay, so what we're trying to do is we want a closed form description of the optimal importance function given, right? So if this was a conditional, if this was just the previous one where it was just xn given xn minus 1, we would be done already, right? We know exactly how to handle that. But the optimal importance function is probability of xn given xn minus 1 and yn, right? So we have to, what we want is we hope to have a closed form for this. And in this very specific case, we actually can. But it's not trivial. So first, what we have to do is we have to use Bayes' rule. So if we use Bayes' rule, we can actually write this like this way, right? Actually, so how did I get from here to here? Because if you use, what would I get with my basic Bayes rule? Right, so I start here and I want Bayes rule. What do I get?
You get the joint over the distribution of the given.
Right, right. So when I say it comes from Bayes rule, I think you see that it's not just Bayes, right? If you just use Bayes rule, this is what you're gonna get, right? Which is this is not the same as this. So here, obviously the denominator is not the same. So what happened? Like, what did I do to get from here to here? But these things have to be equivalent, right? Otherwise, I can't keep using equal signs. But I know for a fact that this thing.
Oh, you use conditioning to pull out the n-1 trajectory, xn-1.
Yeah, right. So what I can do is, instead of keeping these the way they are as the joint, I can write the denominator as the probability of xn minus 1i times the probability of yn given x of n minus 1i. Right. So obviously, since in this form, I don't have this, that means that in the numerator, I must have put out an x of n minus 1i as well, right? In which case, these two would have canceled, and that's why I don't see this form, right? So up here, I could have written as, right? That would have been step number 2 to go from the most direct way of Bayes rule to this form. These two would have canceled, and you see that I had to do a little bit of massaging here to get from this joint conditional to this form, right? So that is to say, this comes from Bayes rule, but it's not like you look at this and you immediately jump into this form, right? You have to do a little bit of a translation to go from there to there. But the reason we want to write it in this form is because based on the way we give our state space model, it's very easy for us to look at this and come up with the likelihood function and also the state distribution, right? So what I need in order to get the optimal importance distribution is I need to know what is the probability of xn given xn minus 1. Right. That would be this term here. So in this model, what is this distribution? Right. This looks, I mean, it's like the previous example, except even simpler because the measurement model is actually a linear function.
Is it a linear Gaussian?
Okay, so it's a Gaussian. Okay, so then I should have a mean and a variance, right, or covariance. So what's the mean?
G times x of n minus 1.
Oh, this is so this is a function. Yeah, I know it looks, so this is a function g taking in the parameter xn minus 1, right? So it's not times, but oh,
So
I know.
whatever your function is, g of x of n minus 1.
Yeah, so g of x n minus 1. Is that it?
Yeah.
Okay, good. And then what's the variance?
QWN.
Right, right. So exactly the same as before, right? Other than this function is not specified, right? So the mean is this value plus the mean of the noise. The noise has 0 mean, so the mean is just this value. The variance, again, all the randomness of xn comes from this noise, so it's Gaussian, and the variance is QWN, right? So this is why we like working with the state transition distribution, because the way we set up the problem is a Gaussian, right? And similarly, you can do the same thing for the measurement. So you know that the probability of yn given xn and I is also Gaussian, except this is going to be h times xn, and then the variance is going to be qvn, right? So at least in 2 of these terms, we know exactly what this thing is, right? So we have a Gaussian times a Gaussian. Okay, so we'll talk a little bit more about this on Wednesday, and then I'll finish our particle filters, and then we'll move on to this thing called the hidden Markov model, and hopefully I'll get to recurrent neural networks. So I'm hoping to give the project out by Wednesday at the latest. Okay, so any questions?
Nope, all good.
Okay, then I'll talk to you guys on
Okay,
Wednesday.
thank you.
Okay, see ya. Bye. Take care.